In this video, we will discuss the solution to problem C, Hungry Games from Codeforces round 959, which was a div 1 plus div 2 round. If you are a beginner to prefix sums and one-dimensional dynamic programming, this is an excellent problem for you to get started on the topic. I believe that this is like the hello world of one-dimensional dynamic programming in the Codeforces realm. Let's move on to the summary of the problem. You are given an array and you need to find out the number of subarrays that satisfy a particular condition. And the condition is that if the subarray is L to R and you start from the left endpoint and you keep going to the right while adding up all the elements that you encounter, and as soon as your sum hits more than X, you reset the sum counter to 0. And then you start the process again, you reset the sum counter to 0. As soon as you reach the rightmost endpoint of the subarray, if the sum is still non-zero after applying operation 2, you will say that the subarray is good. So you need to find out the number of good subarrays that will exist in the array. If you look at the constraints, you will see that n ranges till 2 into 10 to the power 5. So naturally, you need to come up with a linear time solution or an n log n solution. But first of all, we will come up with a quadratic solution, and then we will apply some textbook optimization to improve the time complexity to n log n. Let's talk about the idea that is involved in this problem. Since a subarray is defined by two endpoints L and R, let us try to fix one of the endpoint L and then see how many valid R exist for this particular endpoint. So if we can do that, so if we can consider every element as the starting element of the subarray, then we would have considered all possibilities, right? So you suppose that this is the left endpoint, and then you check which R is valid and which is not valid. So how do you accomplish that? So let's not worry about optimizations at first. Let's come up with a very brute force approach that definitely works. So if this is the left endpoint, first of all, you will keep on going to the right as long as your sum is less than or equal to X. So you keep on going from left to right as long as your sum is less than or equal to X, because you are not violating any conditions. But as soon as you reach a point where this sum is strictly greater than X, so suppose this is the point that you reached where the sum is strictly greater than X. So you can say that this particular endpoint is a bad endpoint, because if you stop your subarray over here, this sum would be 0 and condition 2 would be violated. But all the other elements that you encountered in between, you can end your subarray in this range and the condition 2 will not be violated, because the sum was strictly or less than equal to X in this area. So this is the first bad subarray. So let us color it in red and let us call this as a checkpoint. So this is a checkpoint. This is a checkpoint. Now what happens once you hit a checkpoint? If this is a checkpoint, this is naturally a bad subarray. But after this, you will reset the counter to 0, and it is just like starting your subarray from here and then continuing to the right until you hit the next checkpoint. So this is your next checkpoint. So can you notice one thing? If you can define a DP that counts the number of checkpoints that exist for a particular left index L, then you can compute these checkpoints using the DP value of other indices. Because if this red element is a checkpoint for this box, it also has to be a checkpoint for this box, right? Because if you are starting from here, it is equivalent to starting from here. So let us define a DP where you say CP count. So CP count stands for the checkpoint count. So you say CP count of L is equal to the number of checkpoints, that is the number of red nodes on the right is the number of checkpoints to the right of L. So if CP count is the number of checkpoints to the right of L, to compute this number of checkpoints, you can see that you can find the first checkpoint manually by iterating from left to right. So you can find the first checkpoint manually, and then you can use the checkpoint count for this element. So the recurrence would be as simple as CP count of L is equal to 1 plus CP count of R plus 1, where R is the location of the first checkpoint that you will compute manually. So now you see that to compute this DP value of L, you need to find out the DP value of some index that is on the right hand side. So if you apply a trick of computing the DP from right to left, so if you compute the DP array from right to left, then by the time you are computing the checkpoint count for this particular element, the checkpoint count for this particular element would already have been computed. And that is all you need to solve this particular problem. So we will go over this approach once again just to make sure that you have the idea ingrained in your brain. So we will color all the checkpoints as red. So if this is a checkpoint, what happens after a checkpoint? So you know that everything is reset to 0 once you hit a checkpoint. So if this is a checkpoint, we do not care about what element exists to the left of it. Then after the checkpoints, this is the first element after the checkpoint, then the sum will increase, and at this point, if the sum has become strictly greater than x, we will mark this node as red. So this is the second checkpoint. Then this is the element that is after the second checkpoint, the sum will increase and then it will increase to more than x. So we will mark it as the third checkpoint. Then continuing the process, the sum will increase. So this is the element next to x, and this is the last checkpoint, suppose. So you can see that for this particular element L, every index on the right is a valid subarray except the elements that are colored in red, because they are the checkpoints. And how do you count the number of checkpoints to the right? You can simply brute force the first checkpoint, and then you can say that the number of checkpoints to the right of this element is equal to the number of checkpoints to the right of this element plus 1, right? You can clearly see from this image that if you can get the number of checkpoints to the right of this element, you can simply add 1 to get the number of checkpoints to the right of this element. So once you have the number of checkpoints and you know that all the checkpoints are invalid, so for each particular L, there are n minus L elements on the right, and then these are all the possible choices to create a subarray. You can subtract the checkpoint count minus CP count of L, and then you can sum it up for all the indexes that you have. So now let's move on to the implementation for this particular problem. Yeah, so let us implement this idea from scratch, and let me increase the font size as well so that it is visible to you. Right, first of all we will extract the size of the array, and then let's create a DP array that counts the checkpoint. So CP count, checkpoint count, and we initialize it with 0. Then we fix the left endpoint, so L goes from 0 to n, L plus plus, and for each left endpoint let us locate the first checkpoint manually. So I can say sum is 0, and then I iterate on the checkpoints. R is equal to L, R is less than n, R plus plus, and then you do sum plus equals to A of R. You are summing up all the elements as soon as you encounter, and as soon as the sum exceeds X, you know that you have located the first checkpoint. So you can say CP count of L is equal to 1 plus CP count of R plus 1. But R plus 1 can go out of bounds, so you should only access it if it exists. So you can add a ternary operator saying if R plus 1 is less than n minus 1, only then access it, otherwise set it to 0. So now that you have computed the checkpoint count on the right of each index, and each checkpoint is a bad index, right? So to get the answer, you can say answer is 0 for, then you finalize the left endpoint, let us call it as L, and for each element what are the possible choices, what are all the possible choices? So all the possible choices are n minus L, because if you consider 0 based indexing, for L is equals to 0, all the rightmost index are possible choices including 0. So these are all the possible choices, and then you need to subtract all the bad choices. Bad choices are the checkpoints. So CP count of L, right? And then you just print the answer. Okay, let's compile the code. So I need to add a question mark over here, which is fine. So 830511. Something is wrong. So we are doing this sum plus equals to E of R. Okay, so we actually need to break over here as soon as we hit the first checkpoint, because we have computed the answer. Okay, 830511. Okay, so sorry, here the condition should be r plus 1 less than n, right, for it to not go out of bounds. Okay, sum is equals to 0. N minus L minus checkpoint count of L, which is correct. Okay, let me look at my original submission. What are we missing? G is greater than X. Oh, okay. So yeah, one important thing that we are missing is that we need to populate all of this from right to left, right? Otherwise, how are we using the CP count of r plus 1 if it hasn't been computed yet? Okay. So here, since we are iterating from left to right, that is incorrect. I actually need to iterate it from right to left. Okay. Let's see if it works this time. Okay, 8 to 0 10 7. Okay, so now let's submit this code. Go to submit code, problem C, this. So you will see that it gets TLE on test case 4, which gives us a hint that our idea was correct but maybe inefficient. So now the only optimization that you need to do is that you are computing the first checkpoint manually, right? But you don't really need to do that, because when will the first checkpoint be? So the first checkpoint will be where the sum of this subarray grows to strictly more than x. And since the array contains only positive elements, you know that the prefix sum subarray, so you know that the prefix sum vector is sorted. So you can perform a binary search on that vector to locate that first checkpoint in O of 1 instead of computing it in O of n. And how do you do that? So you can see that the formula for the sum is what? Pref r minus pref of L minus 1, right? This is the sum, and this sum should be greater than, strictly greater than. This sum should be strictly greater than x, right? Because then the condition would be violated. So we are looking for the location r such that prefix of r is strictly greater than x plus prefix of L minus 1. So this integer, this number is nothing but the offset that happens in prefix sum problems. So you need to find this location, and since this array is sorted, you can use the upper bound function. Why upper bound? Because you need to find the strictly greater than. So that is all we need to do to locate the first violating index, that is the first checkpoint. So what I'll do is I will remove this code from here, or let's remove it later. To find the first r, that is the first checkpoint, you can say that r is nothing but, first of all you need to create a prefix sum array. So you can say prefix of n, and then prefix of 0 is 0, sorry, a of 0, and then you populate it. Prefix of I is equals to a of I plus prefix of I minus 1. Okay, and then you need to do an upper bound on the prefix sum array, because it is sorted. So prefix dot begin plus L prefix dot end. So why are we adding plus L? Because we only need to search from starting from L, right? We don't need to go behind, but that is fine. If you don't even add plus L, it should be fine, because I think you can add a condition later that the R should be greater than L or something like that. Okay, and here it would be X plus the offset, and the offset is nothing but Offset is nothing but pref L minus 1. But you know that you cannot access an index L minus 1 if it doesn't exist. So you can say if L exists, so this is fancy way of saying that if L is strictly greater than 0, then take prefix L minus 1 as offset, else take the 0 as offset, right? And once you have this R, you can simply say that if this R is less than N, then you can add this condition over here. Right, and you can delete this code from here. So why is it complaining? Okay, so because we have not added this prefix, and it says, and here we need to subtract the beginning iterator. So minus pref dot begin. To get the index, we are subtracting the starting iterator. We compile the code. Let's see. So 820.10.7, is that correct? 820.10.7. Okay, let us submit the code. So you will see that this time it will get AC, right? So you saw that this problem was like extremely by the books, right? Like you don't even have to think about anything. Like I have seen these kind of problems multiple times in the past. And in fact, this idea that you see, right, of checkpoints leading to another checkpoints, this is a pretty common idea, and this idea is actually used in the stock span problems and finding the next greater element, because this checkpoint will lead to this checkpoint will lead to this. So I think even lead code has a problem called jump game that has something similar to this, right? So that is why this problem was pretty standard, and it is something that you can implement within 5 minutes of seeing the problem. If you want some more practice problem on this topic, you can take a look at a video that I have added on my channel, that was on this same idea of jumping from one index to another index, right? So if you go to my channel, so this is the video optimizing DP with monotonic stacks, and here you will see that this idea of jumping from one checkpoint to another checkpoint is very powerful, and actually it can be applied to more difficult problems. And regarding the optimization, you saw that the optimization that we did from O of n square to O of n log n was nothing fancy, right? It was something that anyone can do if you know the fact that prefix sum of a positive array is sorted.